Welcome back, everybody. In this section, we finally do it. We talk about metamorphic rocks, so let's get started. So the first thing we need to do here is talk about how we're going to group these metamorphic rocks, and the best way to do this is by texture. We have some that are foliated with some kind of layering to them, and some that are non-foliated, no layering at all. Now, in the ones that are foliated, we start with our mud rock. This is going to be our parent. We start with something that is a shale, mudstone, or siltstone. We expose it to gradually more temperature and pressure, and it becomes a slate. If we take a slate, we expose that to more temperature and pressure, it becomes a phyllite. More temperature and pressure becomes a schist, and even more temperature and pressure becomes a gneiss. You have this sort of series of rocks all along the same line whenever the metamorphic grade increases. And what do these actually look like? So a slate tends to be the closest one to the original mud rock. Other than the rock cleavage and the sort of smooth surfaces, it would be difficult to tell that you were looking at a slate and not the original parent rock, some kind of a mudstone. Now we take a slate, we expose it to even more heat and pressure, and now we have something called a phyllite. It has this sort of sheen to it. It has a little bit of slaty cleavage, but not quite. It's a little bit shiny, but not quite like a schist. So if you have a schist in your hand, the best way that you would know what you were looking at is it's shiny. It almost looks metallic in terms of the way that it reflects light. It tends to be dominated by these flat, platy minerals. The micaceous minerals has somewhat of a scaly foliation to it. If you repeat the process again, we take a schist and give it even more heat and pressure. It's going to become what's called a gneiss. This is the one which has the banding, those alternating bands of light and dark minerals. Now, grain size is a part of this. As rocks are subject to increased amounts of metamorphism, the individual grains or crystals sometimes start to glob together. So, grain size tends to get bigger as you work your way down, work your way through increasing grades of metamorphism. By the time you get to gneiss, you have something with usually pretty big mineral grains that are going to be visible to the naked eye. So now we're going to get to the non-foliated side of things. You can look at your textures here and you don't see any kind of a pattern to it, no layering. First we have marble, then quartzite, and then anthracite. So marble is what happens whenever you take a limestone or a dolostone, something that is kind of like a limestone, and you put it through the metamorphic process. Marble is the result. Yes, this is the same marble you have heard of. Quartzite is the result whenever you take a quartz sandstone and you put it through the metamorphic process, increased heat and pressure. The quartz grains start to fuse together and get larger. The result is this very hard, purpley looking rock, scientific term. Finally, anthracite is really high quality, high grade coal. It's what happens whenever you take a lower grade, less quality coal and you put it through the metamorphic process. Unfortunately, or fortunately, depending on how you look at it, most all anthracite coal in the entire world has actually already been mined out. So as a geologist, or as somebody doing geology, you start with the rocks first and then you work backwards from the rocks to figure out something about the history of an area. But what does that exactly look like for metamorphic rocks? Well, metamorphism changes the mineral assemblage, mineral combination that you have in some sort of a rock. But not all the minerals here are equally important. Some of them, like quartz, are going to be found in all sorts of different rocks. What you're looking for are special minerals called index minerals. So if you take a metamorphic rock and you spot the index mineral, that mineral is the one that reveals what the conditions were like, the heat and pressure conditions were like, whenever that rock was metamorphosed. So then you could work backwards from what you see in the rock to the original conditions where that rock formed. And now would be a good time to tell you that the next digit in the access code is 8. The second digit is 8. Second digit, 8. So this chart has a lot of our common index minerals on it. The certain minerals that tell you the most about the original conditions where a rock formed. Now you notice, right, we have low-grade metamorphism here, high-grade metamorphism on the right. Something like quartz or feldspar, these are going to be present throughout any sort of range. So you pick up a metamorphic rock and you see quartz in it, that doesn't really tell you much about the conditions where that rock formed. On the other hand, things like chlorite, this green mineral, muscovite or biotite, which are these light or dark platy minerals, garnets, starlights, these other sort of uncommon minerals, These tell you a little bit more about what kind of metamorphic environment the rock was in. Okay, so in this section, we talked about some of the common types of metamorphic rocks: slate, phyllite, schist, and finally gneiss. We talked about marble, quartzite, and anthracite, our main players in the metamorphic rock universe. We also talked about these index minerals, the certain special minerals you look for in a metamorphic rock that tell you the most about the conditions where that rock formed. In the next section, we're going to go into a little bit more detail about exactly where and why metamorphism happens. These are our metamorphic environments.